Hello my dear viewers. In this short presentation I'm gonna show you how OpenAI can help you to solve a real-world problem, especially how it can help you to boost the language learning so you can learn faster and you can learn with a fun, which actually you could be engaged in the learning. No boring grammar, no memorizing words out of contents, just a seamless reading experience. Here in this animation you see the two versions of the same book that I purchased on Amazon. One is in Russian, my native language, and another is Spanish edition. So when I tried to read them separately, I found myself that it's very difficult to constantly switch from the book to the vocabulary when I found some words and grammatic constructions that I'm not yet familiar with. And I had an idea. What if I can somehow merge these two books into one seamless bilingual experience so I can learn a few sentences in my native language and then read exactly the same sentences but in a target language. And that's how this project was born. You might ask me, hey, it's not that difficult, like why don't you just use automated translation? I can write a Python script within 20 minutes that will do automated translation of chunks of the native language text. But I could tell you that from my experience, the translation doesn't perform well with the literature. You're not going to enjoy reading this. So basically, in this project, you wouldn't find any automated translation. All texts are taken from the language editions that have been translated by professional translators, and that's why it would be very enjoyable to read. If you want to know how I made it possible and what technical challenges did I face, stay tuned. I'm gonna explain and walk you through step by step. Okay, now let's move on to the technical part. I'm gonna show you step by step how you can use OpenAI AI language models for semantic alignment of the two texts in the different languages. So the first task that we have is we have to split our Russian edition into smaller chunks. The chunks shouldn't have to be that big, so the reader can keep in mind the context before he will move on to its semantical pair into Spanish edition version. That's why I don't want the chunks to be longer than 300 characters. And in order to split it properly, we're going to use a spaCy library. This is a very popular Python library for text processing. And we need this library in order to split our texts into sentences in a proper way, because we cannot just split it based on words count or based on the characters count, because we don't want the sentence to be split in the middle. We want to preserve the semantic meaning. And this where this library could help us. We split our Russian edition into the list of sentences, and then we increase the size of each chunk until the characters limit is exceeded. So now let's apply this to our text, and let's read our text, our Russian edition text that is stored in this file, and apply this separation. Let's see, let's take a look at the first three chunks that we've got. Okay, so this is the first chunk, this is the second chunk, and this is the third chunk. So if you understand Russian, you will see that they separated in a proper way, and they're not that big and very manageable to keep the context in mind. Let's see how many chunks total do we have. So we have total 51 chunk, and I should tell you that for the demonstration purposes I used a truncated version of the text. So the whole book is way bigger, but I used just a truncated version in order for the processing wouldn't take that long, just for the purpose of demonstration. Now let's split our Spanish version into chunks. During my experiments, I've noticed that some sentences in Spanish are pretty big. Just take a look at this one. This is a huge sentence, and if we will not split it into smaller parts, it will harm the precision of our semantic alignment. Let's split it based on the comma separators. Let's do this. Here is the logic. We just find the comma separator and we split these chunks, and then we add comma at the end of each chunk, except of the last one, which have to be terminated by dot instead of comma. Let's see how did this sentence been broken into smaller parts. Yeah, as you can see, the code done pretty good job. Now we have much smaller and manageable parts, and we're going to use this part to dynamically increase the size of our Spanish edition semantic matching pair. Now let's split the whole text into the sentences, and then split the whole sentence into the smaller parts. So the logic is very similar to what I did to Russian edition, with the difference that we further breaking on each sentence into the smaller parts, as I just demonstrated. Let's read the Spanish text from this file, and now let's see how many chunks did we got. So we have 227 chunks in our Spanish version, and let's take a look at the first 10 chunks. So here's the first 10 chunks of our Spanish edition. Now let's move on to the embedding. We want to do the semantic matching. And why do we need embedding? because we can't really compare the semantical meaning of two texts directly. In order to compare the semantical meaning, we have to embed texts into the vector. So embedding is a process of converting our text to the corresponding vector, and then we can use some mathematical functions to get a score of similarity between the two vectors. And that's why we need embedding, and we're going to do embedding with the help of OpenAI language model. We're going to use this model. So now let's initialize the OpenAI client. You're going to need some credentials. I have my credentials, you will have yours, and then we can use this function to embed our text into vector. So the function, it only receives the text as an input parameter, and we don't even have to specify the language because this model been trained in many languages, and it doesn't need any additional parameter as a language, and it will represent our text as a vector. And let's see how it works. Let's try to embed the first chunk of our Russian edition, and to see what vector did we get. So we're doing embedding, and as a result, we received a vector which has like 1,536 parameters. That's quite a lot. And let's take a look at the first 10 parameters of this vector. Here are the first 10 parameters of this vector. So here how our text is represented. Now, let's use this mathematical function that's called cosine similarity in order to get a score of how similar two vectors are to each other. So once we embedded the first chunk and the corresponding chunk into another language, we receive two vector, and we can use this function in order to determine how similar are they to each other. So the higher score we got, the higher is the semantical similarity of these two texts. Now let's embed the first chunk in the Russian edition and the first three chunks in the Spanish edition. But before we embed them, let's do the manual alignment for the first fragments. So I did this manual alignment in order to get a sense how precise our model is, what score would it give us for the semantical similarity. If you understand Russian and Spanish, you can see that this text is a precise translation of this text, which means that the first chunk in Russian edition is semantically matched with the first three chunks in the Spanish edition. And that's we did manually. Now let's check what similarity score will the cosine similarity give us. So we're embedding the first chunk in Russian edition, and then we're embedding these three chunks, concatenated three chunks in the Spanish edition, and we will see the semantical similarity score. Let's wait until we'll get the score. And as we can see, it's just 0.553. That's not what we want to see, because it doesn't show us strong semantical similarity. But from the manual inspection, we can see that semantical similarity is pretty strong. But why do we get this low score? The problem is that even though the model being trained in several languages, it doesn't perform well when we try to match two texts in different languages. It shows much better score when we try to compare semantical similarity for the texts in the same language. So what we can improve in order to get the better score? Somehow we need a translation of this fragment, and for this purpose we can use automated translation. Let's see which score will we get if we will apply automated translation from Russian to Spanish before embedding. Let's initialize the Google Translator API, and now let's translate before the embedding. So essentially what we have here, we translate it using machine translation, then we embed, and then we compare semantical similarity of the machine translated fragment with the corresponding fragment in Spanish. Let's see if we will gonna get a better score. And now we can see that the score is much better. Initially it was 0.55, now it's 0.86. And the conclusion we can make from this is that we have to apply machine translation before embedding. And I want to emphasize that machine translation is used only for embedding. You wouldn't see any machine translated text in the output version. In output version, there would only be fragments from the Spanish edition and no machine translation whatsoever. It's only part of data transformation. Now, since we can get the semantical similarity score, let's think how we can build the script that will do all the semantic matching automatically. At the beginning of this video, I showed you the demonstration how we use greedy pointer strategy. So basically what we're doing is we're taking the chunk in Russian language, and then we dynamically expanding the corresponding chunk in Spanish edition until the semantical similarity is peaks. And when it peaks, it means that we found the semantical matched fragment. Now let's do it manually for the demonstration purposes. Now we already aligned manually first fragment in a Russian edition with the first three fragments in Spanish edition. So our greedy pointer now is 3, because 3 is the index where we stopped processing for our Spanish edition. Now let's take the first fragment in Russian edition and calculate the semantical similarity score for this index range in Spanish edition. Let's wait. Now we get score 0.85. That's pretty good score, but let's check if we can do even better if we expand our Spanish fragment by 1. So before we had 3 to 4 index range, now let's test 3 to 5 index range and see what results will we get. Now we do even better, it's 0.9, so this is a better match than the previous one. Let's expand it by 1 and see if we can if we will get an even better score. No, from now we can see that the semantical similarity score is dropping. It means that the semantical pair is lies in this index range. And now let's do the manual inspection. So here's the Russian fragment, here's the Spanish fragment. If you understand both languages, you can make sure that they are semantically aligned. So this is the algorithm that we can use for our semantic alignment. And later on, I will show you how to write a script that will do all this semantic alignment automatically with a very minimal manual interventions, and then can build our dual language book. Now, let's move on to the script that will do the complete semantic alignment of two texts. First of all, I have to introduce the Pandas library. So the Pandas library is a very popular Python library that is used in data analysis to create data frames. And we need Pandas here because we're going to have to represent our text as a data frame that will facilitate the operations and the backup of our data. So before we have our Russian text chunks just in the form of list, but the problem is that we cannot effectively store the list in the file to the backup, and we can't really assign different columns to the data that we have. Because in order to optimize our process, first of all, we're going to need to make automated translation for every Russian chunk, and then we're gonna need to embedding after automated translation. And we don't want to have like many lists with different names. We want to have all our data connected and serialized within the same structure. And Pandas is very handy for this task. Let's create a Pandas data frame, and it initially gonna have only one column, and the column will be called chunks, and this column will have the same values of our Russian edition chunks. And let's check the shape of our data frame. So the shape of the data frame shows us how many rows and how many columns it has. So for now we have 51 row and 1 column. Now let's add automated translation for every chunk from Russian edition. For this purpose, we're going to need to use some concurrency features of Python, and we're going to use multiple threads in order to speed up our translation process. And we're going to use the Google API translation, the function I showed you before, but now we're just using thread pool in order to do it within 10 threads, and this is going to help us to speed up the process. So we're defining this function, and now let's get translation for each chunk column in our row chunks data frame, and then assign this value to translation column. Let's do this, and we can see the progress. We can see the translation being made, and now let's check the shape of our row data frame. Now, as we can see, we have 2 columns instead of 1 because we have a translation. Let's see what the data looks like. As you can see now, the data frame have 2 columns. The chunk is the original column, and the machine translation is another column. Okay, now since we've done this, it's a good idea to back up our results. So in case that we will have to reload the kernel of Jupyter, we wouldn't have to make all these API calls over and over again. We can just take it from this data file. So the Pandas provide a very handy function that's called toPickle, and it will dump all the data from this data frame into binary file. And whenever we want to restore, we can easily restore it. So after you use a lot of API calls to fill in your data frame, I always recommend you to make a backup, especially if the API is not free, if you have to pay for all these API calls. Now, we have 2 columns, chunks and translation. Now we have to add a third column that we'll call embedding, because we want to embed the machine translation in order to compare it later on with chunks from Spanish edition. We're going to use the same logic with multiple threads to speed up the process, and for each value in translation column, we're going to call OpenAI language model to embed it. Let's do this. Now we can see the progress. Okay, so all columns are embedded, and let's add the embedding column to our data frame. Now let's check the shape of our data frame. So now it has 3 columns, and let's take a look at the data. Now it has chunk, machine translation, and embedding. And since we used an extensive amount of API calls, it's a good idea to do the backup to store our data frame into the binary file. So we won't have to pay for all this API call over again. And the next step. Now, once we had the embeddings, we have to find the corresponding fragment in our Spanish edition. And how we're going to do this? As I explained you before, we're going to use a greedy point strategy. And the logic is within these functions. So we have embedded values that we will take from this column, and we have a pointer that is the current value of greedy pointer. So what we're going to do, we will dynamically expand the size of our Spanish fragment chunk by chunk until our semantic similarity score is peaks. So once it peaks, we will break the cycle and we will return the value of pointer that we found. That's how we're gonna find the semantic match. Okay, now let's move on to the main logic. The main logic of alignment is contained within this function. Let me explain a bit the logic. So by using greedy point strategy, what we exactly doing? We're just walking through the fragments of a Russian edition one by one sequentially, and for each fragment we're looking for semantic match in a Spanish edition. But we need to implement some additional logic for retracement. So what is retracement and when do we actually need it? Because the cosine similarity score is not very precise. So it happens occasionally that the fragment, the previous fragment accidentally grabbed the chunk that needs to belong to subsequent fragment. If we will not correct it, that we will lose our alignment forever and the process won't be able to finish. For this reason, I have implemented this logic. So we're trying to get like the best similarity score, and if the best similarity score had its peak when it was less than 0.6, it means that we failed to find a good semantic alignment for this particular fragment. And what it means? It means that probably the previous fragment have grabbed some chunks that shouldn't belong to him, and then we need to do a retracement. When we do the retracement, first of all, we try to go backward for no more than 5 chunks and to compare our semantic similarity. So in case that our chunks have been accidentally grabbed by the previous item, we going backwards and we might be able to find semantic similarity and to fix this problem and to restore our alignment. But if it didn't happen, it means sometimes that we might go forward. And when we have to go forward, let's say when translator for some reason inserted some sentence that doesn't really have a semantic matching in another edition, so sometimes we need just to skip it, and for this reason we're just going forward. And if we failed in both ways, forward and backward, then we'll have to stop the process and then we'll have to realign it manually. And it didn't happen very often. It happened maybe once in 100 chunks. And the reason why it happened, because sometimes the sentences are semantically matched, but for one particular case we're just getting a low score in cosine similarities and we have to manually adjust it and to restart the process. But again, the manual intervention is very rare, just once in 100 fragments. Now let's start this function and let's see the process. Let's see how it goes. So now the process is started, and as you can see, we're getting a pretty good score for our fragments. This gives us a lot of confidence in our code. Now we see the first retracement. So as you can see, the algorithm was able to fix alignment by doing retracement for the fragment 5. And every 10 fragments we doing a backup, because it's important. If our process will be interrupted for whatever reason, then we can just restore the data from backup. We don't have to do it like all over again. Let's see if we will get any more retracements. The process is not that fast, but yeah, I mean, we cannot do it in parallel because we use a greedy pointer strategy. But if you have a book that is divided by chapters, then you can do it in parallel for each chapter. But I picked the book that doesn't have any chapters, so the only way to run it is sequential. We see more retracements. Now we can see as a retracement for fragment number 30. So as you can see, first of all, it tries to go backward, and now it didn't get a good similarity by going backward, and it started going forward. And so on and so forth. And if we'll have a lot of patience, we're gonna have the whole book aligned. Now let's stop the kernel and to see what it looks like. Okay, we stop the kernel and let's see our data frame. So we have an original chunk in Russian language, then we have automated translation, then we have embedding, and then we have the matched fragment in the Spanish edition. And that's how we can reconstruct the whole book. Now, after we interrupted the kernel, let's take a look at the results of our semantic alignment. So I'm not gonna show the first fragment because we already seen it. Let's take a look at the back of our list since our semantic alignment being interrupted at fragment 36. Let's take a look at their items from 15 to 30. So these fragments been aligned automatically without any manual intervention, and that's how our dual language book will look like. So we have the sentences in Russian and in Spanish, like one by one. Let's even try to read it from the beginning. Хосе Аркадию Буэндия, который не мог успокоиться после провала своей затеи с магнитами, тотчас сообразил, что это стекло можно использовать как боевое оружие. Melquiades снова попытался отговорить его. José Arcadio Buendía, que aún no acababa de consolarse por el fracaso de sus imanes, concibió la idea de utilizar aquel invento como un arma de guerra. Melquiades otra vez trató de disuadirlo. And this way I can read the sentence by sentence and to remember the context and to improve my grammar and vocabulary. That's very, very efficient learning process, and that's how I can combine the book. As the next stage, I'm going to show you how to translate this into the audiobook in 2 languages using Google Text to Voice API. And now moving on to the final part, let me show you how we can convert our semantically aligned sentences into audiobook. The advantage of audiobooks is obvious because you can combine it with any other activity, including physical activity. For example, I can listen to audiobooks when I'm working out in the gym, or when I'm cleaning in my house, or when I'm walking in the park. And to convert our sentences into speech, we're going to use Google Cloud Text-to-Speech API. In order to use it, you need to register there, and you need to create your project, and you need to make sure that Text-to-Speech API is enabled for your project. But you can read about it in the documentation. It's out of the scope of this video. For now, I have my client already prepared. Now let's give instructions to text-to-speech API. The instructions are provided in the form of XML document where you have to specify the voices that you want to use, and you need to wrap your sentences into the tag that had a voice parameter. So here we use this voice for Russian sentences and this voice for the Spanish sentences. And that's how we are building our XML document from the semantically aligned structures that we have already. Now let's take 3 semantically aligned chunks and to prepare XML document to convert them to audio. Here what it looks like. So we can see that Russian sentences are wrapped into Russian voice tag, and the Spanish sentences are wrapped into Spanish voice tag. And since we already have instructions, let's use Google Cloud API to get our audio file. Let's do this. Let's wait until it converted to the audio. Yeah, now it's already converted to the audio file, and we can open this audio file.
Хосе Аркадия Буэндия, который не мог успокоиться после провала своей затеи с магнитами, тотчас soобразил, что это стекло можно использовать как боевое оружие. Melquiades снова попытался отговорить его.
José Arcadio Buendía, que aún no acababa de consolarse por el fracaso de sus imanes, concibió la idea de utilizar aquel invento como un arma de guerra. Melquiades, otra vez, trató de disuadirlo.
Но в конечном счете цыган согласился отдать ему лупу в обмен на 2 магнита и 3 золотые колониальные монеты. Урсула рыдала от горя.
Pero te reinó por aceptar los 2 lingotes imantados y 3 piezas de dinero colonial a cambio de la lupa. Úrsula lloró de consternación.
Эти деньги пришлось вытаскивать из сундучка с золотыми дублонами, который ее отец копил всю свою жизнь, отказывая себе в лишнем куске, и который она хранила в дальнем углу под кроватью в надежде, что подвернется счастливый случай для их удачного применения.
Aquel dinero formaba parte de un cofre de monedas de oro que su padre había acumulado en toda una vida de privaciones, y que ella había enterrado debajo de la cama en espera de una buena ocasión para invertirlas.